Hey everybody, welcome back. So this time we're going to be talking about heat pump systems. Now the most common one you're going to see is simply air-to-air, which is outside many of your homes, including mine. The reason for this is simply because it's really easy to install. You have air outside your home, you're able to send heat or steal heat from that air. However, that's not the best system. You can also use water source systems or ground source systems to either pump heat into your home or pump heat out of your home. And they have a lot higher coefficient performance, but they're a lot more expensive to install. Why? Because you have to get some sort of pipe into the ground or into that water source to then take the heat or put the heat there. And so that's where you start increasing your costs. If you can do that, like if you're building your home, go ahead and install a ground source geothermal heat pump, and you will be saving tons of money. Now, one question you might have is like, let's just go with ground source for now. Why are ground source so great? Well, the reason for that is because while the air temperature outside your house is going to fluctuate quite a bit, maybe up to 100 in the summer and down to 30, I'm in America, so Fahrenheit, in the winter. The ground, however, is always about the same temperature. It's about 55 degrees Fahrenheit, or roundabouts. Depends on where you are, it will change a little bit. And that's the same in the summer and the same in the winter, which means that in the summer it's great for cooling, in the winter it's great for heating. So why do we like that? We like it because your heat pump is less effective at low temperatures. Specifically, we learned that the coefficient performance, it drops dramatically when I have a much higher temperature difference. So the bigger that delta T is, the smaller my coefficient performance. And so since I typically keep my house above, freezing, when the air gets freezing outside, it's really hard to heat that way. That's why for most air source heat pumps, not for ground source, but air source, you're gonna have some sort of supplementary heating system. I use a furnace, you use something else, all's fine. So where do you want to use a heat pump? Well, it's best in places that have a really large cooling load during the summer or whenever you're trying to keep your house cold, but a relatively small heating load during the heating season. So terrible summers, but mild winters, heat pumps are your go-to. And in those kinds of areas, it's great for commercial or residential. Another cool thing is it's all the same technology. I just love this. Like all you have to do is you spin around and you're doing it in the opposite direction. But it can heat your home or it can cool your home. So if you have a heat pump and you're in one of those areas, you can use the same system to do both. Let's say you're in an area that has really bitter winters and also really terrible summers. Yes, you could use a heat pump, then you have to use a furnace during the winter. You're going to use two systems. But in those places where you have those mild winters and the really hot summers, heat pump works great. Now, this is already pretty short, so let's go ahead and do an example. So we have a heat pump. It's using refrigerant 134A, Freon, and it's heating a house using underground water at 8 degrees Celsius. I wish mine did. That's the heat source. Okay, heat source, 8 degrees Celsius. The house is losing heat at a rate of 66,000 kilojoules per hour. The refrigerant enters the compressor at 180 kilopascals and 0 degrees Celsius and leaves at 1.6 megapascals and 90 degrees Celsius. Refrigerant exits the condenser at 36 degrees Celsius. Okay, we got a bunch of information right there to help us figure out what our states are for all those points. We want to figure out what the power input is to this heat pump. Okay, so first off, let's do a picture. So here it is. Here is my heat pump. It's in heating mode because that's what this one says it's doing. And so we know, let's see here, what's entering the compressor. So going right there. We know what's exiting it. And we're knowing what exits the condenser. So right here. Right here. There you go. Okay. I think I put all this in the right place. If I didn't, we'll see. Okay. So now let's go ahead and label things. So we're going to call what's entering the compressor number 1. We're going to call what's exiting the compressor number 2. What is exiting the condenser number 3, and what's entering the evaporator number 4. So I've totally put my condenser in the wrong place. This is the other place we know. So now we're going to work through what's given in the problem statement. So first off, for number 1, point 1, right entering the compressor, it says it's 180 kilopascals, 0 degrees Celsius. I always tell my students, if you have nice round numbers, it's probably superheated. The way we can check is simply saying, okay, for this pressure, what is my saturation temperature? Well, it's lower than 0 degrees Celsius, so that means this has to be superheated. And so from that, I can go ahead and find my enthalpy. We want enthalpies here. This is how we're going to figure out the power input, sorry. Okay, that one's done. Let's go to number 2. So once again, I can check and see here. Okay, this is 1600 kilopascals. If I check my saturation temperature, I will find that this is too hot, therefore it's superheated again. And so once again, I'm going to be going and looking at the tables. I want to go ahead and show this to you for Freon so you can see this in case you haven't seen how to do this before. So it's a little bit of movie magic. We're going to jump there right now. Okay, so here we are in the appendices. I'm going to jump down to superheated refrigerant 134A. Actually, I'll go to the pressure table first. Okay, so right here is, did you go the right one? It did not go nearly the right one. My goodness, that was terrible. Okay, let's see. How far did it jump? Wow, it jumped really far past. We'll try one more time. Okay, I'm just going to scroll up here because it did not do it right. Here we are, superheated, and then finally pressure table. That was terrible. Okay, so for 1600 kilopascals, the saturation temperature is 58 degrees roughly, 50 degrees Celsius. It says we're at 70 degrees Celsius, so that's how we knew that it was superheated. Right here, we were looking at this. We found the pressure, we matched it, we said, okay, is my temperature higher or lower than the saturation temperature? Lower, I'm a compressed liquid, just pretend it's a saturated liquid. Higher, I'm superheated. So now we're going to go to 1600 kilopascals here. So it's always pressures in megapascals, so it's 1.6 megapascals. And then I'm going to match the temperature. So we'll go down a little bit, and let's see, keep on going, 1.6 megapascals. I go down to 70, I go across. The first one is my specific volume, the second one is my internal energy, the third one is my enthalpy. There's the number. This is how I get it. So hopefully this helps you to understand your tables and also that the HTML is a little bit broken in this one. And let's jump back to the problem now. Okay, and we're back. So, I looked at 70 degrees Celsius. Whoops, it was 90 degrees Celsius. Well, the process is still, or the principle is still the same. So we now have our enthalpy at state 1 and state 2. Now we need to get it at state 3 and state 4. If we have that, we're golden. We've got everything at that point. And actually, it says determine the power input to the heat pump. I don't actually need anything else, do I? Well, we'll keep on going for now. So after going through this coil right here, the condenser, I'm going to become a saturated liquid. A saturated liquid at what pressure? At 1600 kilopascals. And so technically I should have the same temperature as that. So this is going to be subcooled right now. So what I'm going to do is I'm going to say, okay, since you're subcooled, I'm going to say that you are a saturated liquid at that temperature right there, 36 degrees Celsius, even though, technically you're compressed. And so that gives me my enthalpy right here. I just look it up in the tables. I match the temperature. I don't care about the pressure because it's too cold. And I get my enthalpy for that particular temperature. And finally, for the last state, throttling is isenthalpic, or at least we're going to assume it is. And so for state 4, we have that last enthalpy. Okay, now it said, what's the power input to the heat pump? So let's figure it out. As a note, for a heat pump, only the compressor in this particular setup is receiving power. Like in your actual heat pump, you might have a fan that's taking power as well. But for us, it's just the compressor. So now let's figure out the mass flow, because that's the thing we don't know yet. So mass flow is going to be all about how much heat I have to add to my home. I know that I'm losing 66,000 kilojoules per hour of heat, and so I have to replace that. If I don't, my house cools down. So where is heat entering my home? Well, heat enters my home through the condenser. This is where the heat is entering my home. And so the difference in enthalpy between this point and this point is that heat entering my home. So I find the difference right here. I find out how much total I need to be adding to my house. And that tells me my mass flow rate, how fast the refrigerant has to be flowing to really produce that much, to give off that much heat constantly into my home. And so for this, we find that it's 0.0856 kilograms per second. Okay, so now we have a mass flow rate. And so all we need to do now is figure out, okay, mass flow rate times the change in enthalpy across my compressor to get my power input. And so that comes out to be 5.3873 kilowatts. That's just my change in enthalpy times the mass flow rate, because what's causing that change in enthalpy is the compressor. Okay, everyone, hopefully this helps you to look at a heat pump and understand how you can calculate its performance. If you got any questions, leave a comment. Thanks so much. Goodbye.